Right. So we saw one side of the local Langlands bijection. So let's see the other side. So the word representation is showing up again, but this is a very different kind of representation. So these representations are a different nature. So it's a warning, almost all in stark contrast to the previous few lectures. Almost all representations here are going to be infinite dimensional. So when I was your age, that idea kind of terrified me. And one of the goals, really, today and maybe tomorrow, is I want to give you some very, very explicit examples of infinite dimensional representations of infinite groups, and convince you that actually these things one can really work with them. You know, I'm going to ask you questions about these infinite dimensional representations, and you'll find that you can actually answer them. Right. So as ever, we want E a field, and I guess, well, so let's have E a field. And again, let's put the discrete topology, right? Discrete topology. For Wedeline representations, E had to have characteristic 0 because I needed to make sense of norm of something. But I think here I just need some random field. I don't think we need norms yet. So let's have V over E, a vector space. Okay, so infinite dimensional is fine. And of course, we've got K over QP finite. And I want to consider, the obvious, right, so I'm going to put the discrete topology on E so V is going to have the discrete topology and the automorphisms of V is going to have the discrete topology. So I don't need to worry about continuous maps. So pi from GLN of K, so we're doing representations of this group now here, of GLN of K. So that's normally the target of a representation, but today it's going to be the source. So it's going to go to the E automorphisms of V. A group homomorphism, right? So there's no notion of continuity because I want E to be kind of a random field, and I don't want to put topology on E. So I don't really want to put a topology on this. I don't know. I think, anyway, this is the situation. There's too many of these, right? This can't be the right definition. GLN of K definitely does have a topology. Even if I don't care about the topology on E, GLN of K definitely has a topology. And I somehow want pi to be I want pi to respect that topology in some way. So I want a notion of continuity. So there's too many pi's, right? What a sensible notion of continuity. So I'm going to give you two such notions. We say pi is smooth if stabilizers are open. If for all little v in V, stabilizer of V which is by definition the G in GLN of K such that G of V is V, by which I obviously mean pi of G. pi of g of v is v. If for all v and v, the stabilizer is open. Right? So that's, you see, so I'm somehow modeling, I'm modeling the fact that everything is somehow discrete here, and I'm taking a very small thing which is somehow open, and I'm saying its preimage of open is open in some way. I think this might be equivalent. I guess pi, I'm just thinking aloud now, I think a representation of pi, sorry, a representation of gln of k is somehow equivalent to a map from gln of k cross v to v, right? And I'm just thinking that this might be equivalent to, is this equivalent to this map here, the induced map from gln of k cross v to v, continuous? I think it might be, with v discrete topology. I think that's probably a very easy question. I just don't want to get distracted on it now. So there we go. So there's smooth, and that's some very strong notion of continuity. Because I'm not allowed, you could imagine as somehow, if E was the p-adic numbers, then you could imagine somehow elements in here varying kind of p-adically continuously, and the elements here moving p-adically continuously. But E is a random field with a discrete topology. So I've got something moving p-adically continuously here, and the only way it can possibly move over here is just by staying the same. So I'm saying locally, stabilizers being open means that, for every vector you've got a little subgroup of things that don't actually move that vector at all. That's the only way you can move p-adically continuously, is by staying in the same place. So there's some kind of continuity notion, and here's an even stronger notion. We say that a smooth pi. Well, if you're Matthew Emerton, Matthew Emerton's got a little bee in his bonnet about the word admissible, because he thinks admissible is an adverb. So this is what Emerton would say, right? Or just admissible. It's a terrible word anyway. Because it's one of these things, it sort of might have sounded like a good idea at some point, but it doesn't really tell you. Admissible, what does admissible mean? It means it's allowed, right? It doesn't at all describe what the, if I asked you to guess what the definition is, you've got no chance at all, right? What is the definition? It's this: if for all u living in gln of k open subgroup, the things fixed by u is finite dimensional. So just to give you some kind of a feeling as to what the difference between these two notions is. So if I say something is admissible, what I'm now going to do is if I say something is admissible, okay, that's going to imply it's smooth, right? So if I say pi is admissible, right, this implies pi is smooth, you see. So that's just a clarification. So really I should call it smooth admissible. Because you could imagine defining admissible just to be that thing there, and then applying it in situations where pi isn't smooth. So admissible is going to mean smooth and admissible. So just let me give you somehow one example that clarified my thoughts. E.g., if dim v is 1, and then pi of g is just 1 for all g. That's easily checked to be smooth and admissible, right? But let me just make the following note. If I take an infinite direct sum of these, if dim v is infinity, and pi of g is 1 for all g, then this is smooth but not admissible. So this is something like an infinite direct sum of trivial one-dimensional representations. And as a rather tricky result, if pi is irreducible and smooth, that actually implies admissible. I don't know how to prove that, but I'm pretty sure it's a standard thing, maybe due to Jacquet or something. I don't know. Here's a why? Who proved it? I just remember asking. I asked someone at the time. I think I asked Toby G, and he was like, "Yeah, that's some old theorem of Jacquet or somebody." But I think this goes back a long way. Why did I make such trivial remarks? It's just sometimes you'll come up with your own questions, and one of these things here will answer it. Hello.
What's the topology on GLNK?
GLNK has its p-adic topology. Yeah, K has its usual topology in GLNK. GLNK is the units in a ring, right? It's the units in n by n matrices over K, so I can just put the subspace topology on, right? Because we all know that works fine in 99% of cases. So if you like, I mean, I will answer your question. So basis of open neighborhoods. Of 1 in GM. If I have a group and I want to make it into a topological group, all I have to do is tell you a basis of open neighborhoods of 1. Because if you want to know a basis of open neighborhoods of x for some random x in your group, all you do is you take all the bases of open neighborhoods of 1, then you multiply them all by x. Because multiplication by some element is going to be a homeomorphism from a group to itself. So all I have to do is tell you a basis of open neighborhoods of 1 in GLN of K. It's going to be the matrices A, B, C, D in GLN of OK, such that A, B, C, D is congruent to 1 modulo pk to the power n. So no, let's not use n to mean two things. Let's use capital N there. M equals 1, 2, 3. Okay? So we're using that's n is 2. I don't know how that happened. That tells you something about where I feel comfortable, doesn't it? Right, let's have matrices M such that M is congruent. Let's all be grown-ups and do the congruent the identity matrix there. So that's the answer to your question. Smooth, admissible. Oh yeah, so I should maybe say, irreducible means what you think it is, right? If you know anything about functional analysis and kind of like representations of groups on Banach spaces and things like this, you might have a irreducible Banach space representation because there's no invariant closed subspace or whatever. You know, there are fancy, you know, the use of the word irreducible is sometimes perturbed because you might be considering subspaces with certain topological properties. But that's not going on here. This is a very algebraic theory, right? It's kind of amazing that we can do infinite dimensional representations and yet still hope to think about things algebraically. So maybe I should say that pi is irreducible. If exactly the thing you think is true is true. If there is this exactly two invariants, exactly two GLN of K invariant subspaces. Namely 0 and V. Okay, so there's no issue about you have to be closed subspaces or blah, blah, blah. There's no. So it's a very algebraic definition. You see, and at the end of the day, my analysis is poor, right? We haven't seen a single L function yet. I could have defined the L function of some Veidelian representation. I just.
That's exact.
Huh?
Exact.
Yeah, sure. How do you write? So you're telling me that if I write the number 2 on the board, then there might be some instance where that's not exactly 2? Okay. Right. Oh, I see. I see. Yeah. You're right. Exactly 2.
For the online audience.
Yeah. Exactly 2. And the number of GLNK invariant subspaces shall be 2. There. 4 is right out. What should we do now? I've got 5 minutes, but I think we're there, right? So, first vague statement, okay, we're getting there. Of the local Langlands conjectures. For GLN. Right? So what's going on here? I don't really know the history, and it might be interesting to know the history. So we've seen what class fill theory says. Local class fill theory says that K star is isomorphic to WK ab. Right? And what we really want to understand, all of WK, right? So as I say, historically, we knew for a very long time that this group was somehow solvable, and so we understand abelian representations, and so maybe there's a hope that we could understand, we understand the abelianization, maybe we could understand the general, group by making some finite base change and then looking at abelian representations of that. But it was never quite clear what the general vague group should be isomorphic to. And what Langlands' insight was that you can reinterpret this local class fill theory isomorphism Langlands' reinterpretation is that you see the abelianization of a group, that tells you something about one-dimensional representations of the group. So this is Langlands' reinterpretation of local class fill theory, is that these groups are isomorphic, so their representations are isomorphic. So irreducible, one-dimensional representations of K star, and if you think about it, irreducible representations of an abelian group are kind of always one-dimensional, right? So irreducible one-dimensional representations of K star are going to be the same as irreducible one-dimensional representations of WK. And the trick is we're going to generalize the right-hand side by looking at n-dimensional representations, but we're not going to generalize the left-hand side by changing that one to an n. This K star is GL1 of K, and we're going to change that one to an n instead. So that's the amazing insight. So I spent the entire time today carefully writing down definitions. So I think I can finish by at least writing down a statement of the local Langlands conjectures for GLN. So I think I've done everything. I'll have egg on my face if I run into a word I haven't. Yeah, let's see what happens. So local Langlands for GLN. So local Langlands conjectures. For GLN. There exists a canonical that word doesn't have a meaning, right? A canonical bijection let's stick with the same order. So irreducible, admissible representations of GLN of K these are supposed to biject with F semi-simple n-dimensional Wedelin representations. Of the Weil group of K. So what I'll show next time is I'll just convince you that for n equals 1, this is local class field theory. And for n bigger than 1, well, I'm going to talk about the case n equals 2. So maybe I should tell you what we're going to do next. So next time, we're going to stick to the case n equals 2, and I'll show you lots of examples of elements of both sides, right? And so some constructions are pretty easy. As I say, these are possibly infinite dimensional representations, but actually just using a trick of inducing, you can look at induced representations. It's not so difficult to build things on this side. And it's not so difficult to build things on this side. I built one already, right? I built a two-dimensional representation with n not 0. So I'm going to spend a fair amount of time tomorrow building examples on both sides for n equals 2. And then I'm going to match them all up. And I'm going to say, it's canonical. So what are the local Langlands conjectures for GLN? You see, at the minute, it's a rather trivial exercise in set theory to verify that both sides are. So this is everything is up to isomorphism, right? And if you look at isomorphism classes, both of these sets have got the same cardinality as the real numbers, right? So I can just choose some abstract bijection between the real numbers and both sides, and then I can say I'm done. So then somehow the purists would argue that that wasn't very canonical. And so then you can counter by asking them what canonical means. And people kind of struggle. I mean, people say that they know what the answer is, but I'll tell you what people tend to do. They tend to write down a list of invariants on both sides. Do you remember we had this f? Do you remember we had f of row 0? You can define f of something here, and you can define f of something here, and it's a lot of work. And they say, oh, the f's have to match up. It's like, okay. And then you can kind of check that there's kind of 2 to the, you can check that there's 2 to the LF null for each value of f, and you can still cheat. And they'll say, oh, well, no, it can't be that. So people write down lists of properties that this bijection should have. But if you go and look at the literature, one of them is like epsilon factors of pairs, and that's a totally bogus, that's a very strange thing to be doing. Anyway, I'm not happy with the local. This is, in my mind, why it's called Langlands philosophy and not Langlands conjectures, because I don't really know what this word canonical means. But on the other hand, I'll write down things and I'll match them up. And you can see that at least it looks like I'm doing the right thing. So I guess I'll fuss more about canonical next time. But that's where we're going now. I want to prove to you that you understand the local Langlands conjectures for GL2 by giving you a big map of what these things look like on both sides, and showing you that you can really match them up.